Now let's talk a little bit about IP networking and how this information gets from here over to here. Because that's the whole thing about using computers, right? You can have a computer, you can sit down, and you can do some stuff, whatever it is you want to do. Listen to some music, play a game locally, write a paper, write a book, right? People use computers for many, many reasons. I'm going to venture to say some of the main reasons they use them today is to get online, to do research, to play online games, to communicate back with the headquarters, to teach a virtual class online, to watch training videos online, right? So we have to be able to get from point A to point B. That's where IP networking comes into play. So Internet Protocol, or IP, is responsible for sending packets from the source to the destination hosts. It's responsible for showing the way for the data. All right? Now, this is an unreliable protocol. There's no mechanism in place to make sure it's doing what it's supposed to be doing. So it doesn't guarantee that the packets arrive error-free, or if they arrive in the correct order even. That's not IP's job. We have other protocols that is responsible for that. We'll get to those guys here in a second. Again, IP is just responsible for showing you the way. It's the roadmap of how to get there. Because it looks at those destination IP addresses and it says, okay, we need to go out that door, out that interface to get to the next router. And remember, that router is going to grab it, look at the destination IP address, subnet mask, and say, oh, I know what network that belongs to. That goes that way. So it switches it over and pushes it out that door, pushes it out that interface on maybe to the next router, or maybe the computer's down that way. Okay? That's what IP does. It's responsible for negotiating where the traffic goes. It's responsible for the layout, the traffic map, if you will. So in this IP addressing, and we're talking about IP version 4 right now, IP version 4 is 32-bit values. Now these IP addresses, they are supposed to uniquely identify devices on a network. Your laptop, your desktop, your server, a managed switch, the interfaces on a router, your wireless access point you may have hanging from your ceiling or sitting on your shelf over there, your tablet, your phone, your gaming console, your TVs nowadays, your streaming media devices that you may have connected to your TVs, your Bluetooth players. All of these could have IP addresses if they connect to the network, if they connect up to the internet. 32-bit values. You may see it like 192.168.100.100, for example. And we're going to talk about that type of IP address, but I just put that one out there because, well, it's a generic private address. And we're going to see private addresses here in just a second. But I'm venturing to say in your own home, you may have an address that starts with 192.168. It may be 10.something.something.something. Maybe 172.17.something. But most of the time, they stick with the 192.168. Unless you're network savvy, and I hope you are, you could get in and manipulate the information that's coming from, say, your wireless router or your internet service provider on what IP addresses you can have on the inside of, say, your own home, your private business, your small office, home office, or your enterprise for that matter. I used to work at a pretty large business and we had the 10 address, 10 network, the 10 dot, I think it was 10.10.00/16. And that may not mean anything to you right now, but that gave us about 65,000 and some change addresses. It's a lot to work with. So we had that whole network that we could use. But we as network administrators and IT professionals, we decided that. And you can do that in your own home as well. But again, IP version 4, 32-bit address. Now, there are 4 areas in that address. So if you think about it, you got 192.168.100.100. So I had 4 different areas there. Those areas are called octets. And those octets are separated by those decimal points. So again, 192.168 8.100.100. So I've got 4 areas, or 4 octets, that are separated by decimals. Now, if you think about that, you're thinking, well, an octet, that probably stands for 8. And the 8 in this case means there are 8 bits in each one of those areas, those octets. So you can think, okay, there's 4 areas. Each area is an octet, which is 8 bits. So 4 times 8 is 32. That's right. That's where we get a 32-bit number from. Now, each octet has a particular range. We can't just stick any number in there that we want to. It has to be anywhere from 0 to 255. And there are some reserved IP addresses in there. But as far as the range goes, we can have 0 to 255 in each one of those octets. 0000 being the lowest, obviously. And 255.255.255.255 would be the highest. Now, we can't necessarily use those, but that's for a different course. Now, those IP addresses, say 192.168.100.100 again, is broken up into network and host sections. Now, what's responsible for that is called a subnet mask. If you were to put a mask on, right, it covers up your face. Or if you're like the Phantom of the Opera, it might cover up half of your face. And the other part is exposed. The subnet mask does the exact same thing for your IP addresses. You have an IP address, you put a mask on it, you can see the host portion. You're covering up the network. What's covered up, you can't change because it's covered up, right? So you can change what's not covered up. So that's the part you can play with. And so if you go back to what I said earlier, we had the 10.10.0.0/16 network. 16 means that's the network portion, the first 16 bits. So that's the first octet and the second octet. So I had to stay in the 1010 network. But the .0.0, I could go anywhere from 0 to 255 in those ranges, right? So I could have the 1010.1.2 IP address, for example. Or I could have the 1010.255.250 IP address if I wanted to. Me, as the IT professional, network admin usually takes care of that kind of stuff. Server admins or system admins may help with that as well, but that's IP address allocation. Who gets what? We usually have some mechanisms in place, like a DHCP server, to do that for us, but we're not going to get into that one right now. So again, that subnet mask, that's responsible for covering up the network portion of our IP address. That, again, is the part that we can't change. We also use the subnet mask to determine our network range. So if I see what it is, right, I cover that up, just like I said. So I could say 10.10.0.0 all the way, that's my lowest number, all the way up to 10.10.255.255. Because remember, it has a range just like an IP address, from 0 to 255. So that could be my IP range according to my subnet mask. Now, when it comes to IP addressing, sometimes, a lot of the times nowadays, we want to communicate with other individuals. Meaning, surf the web, for example, or talk to your buddy on Skype, or play an online game. Well, if your buddy lives in another country, or another state, or another city, they're not on your network. You need to communicate outside of your network. So what we need to hit is the default gateway, right? We need to take that information and take it from our computer and push it onto the default gateway, because that is going to be the way out of our network, the gateway to the castle, if you will, right? Your home is your castle. So that is the gate to get out of the castle. So you're going to go out the gateway. Now, this happens when we have traffic destined for another network. Now, network admins, they usually configure the default gateway, and everybody has their own way of doing it. Sometimes they use the first available IP address. Sometimes they use the last available IP address. There's no right or wrong way of doing that. But most of the time they follow some of those standards. They usually don't grab an IP address somewhere in the middle or some arbitrary IP address that they have available to them in that range. So going back to my example, our default gateway may have been 10.10.0.1 because that's going to be the first usable address. And that way, I don't have to remember 10.10.24.68. I just made one up, right? That's some arbitrary number right in the middle of our range. But that's harder for me to remember than 10.10.0.1. Because now if I'm network admin or if I'm troubleshooting or trying to help somebody over the phone, I know exactly what that setting's supposed to be. Or it could be 10.10.255.254 because that would be the last usable IP address. So anyway, that's a standard that a lot of network system admins use when it comes to our default gateway. You need to know we have to go out that default gateway to talk to the rest of the world. Now, if you're passing traffic, if you're like me, and this is a long time ago, I guess, 15 years ago, you may have a LAN party, right? I don't know. But your friends come over, right? They bring all their computers, the Doritos and the chips and the Dr. Peppers and everything else, right? And you play games, but you're inside a home. Somebody set up a hub or a switch so we could all communicate. We all configured our IP addresses. And there would be 4 or 5 of us playing games. Well, I don't see kids doing that as much nowadays because of the way we have broadband set up and the way online gaming is set up now. Now they don't even have to leave their seat and they can play games with individuals anywhere in the world. I'm still guilty of that. I still play online games. I got friends in Europe that I play with and all over the place. Well, obviously we're on different networks. So my information house is always passing out the default gateway. Now we have different classes of addresses that I think you need to be familiar with. We have Class A, Class B, and a Class C. We also have a D and an E, but I'm not showing that right this second. You can see here that a Class A, the network portion of that address is the very first octet. That means that we can have very small amount of networks, but the networks themselves are going to be very large. So let's think about this for a second. These are binary numbers. These are bits. It's either on or off, a high or a low, a 0 or a 1. So we're talking about the powers of 2. There's only 2 possibilities. So if we think about that, and we have 8 bits for a Class A network or a Class A address. We have 8 bits that are designated for networks. That's all we can have. So 2 to the 8th power, we can have 256 networks. Now you might think, well, that's quite a bit. But if you think globally, that's not very many at all. However, each network has 24 bits of host space. That's the blue portion that we're looking at right now. So you can see the second octet and the third octet and the fourth octet. They're all blue. Well, that's 8 plus 8 plus 8. 3 times 8 is 24. That's where I came up with 24 bits. So 2 to the 24th power is 16 million and some change. So each one of those networks can have up to 16 million hosts in each one. So even though we have a very small amount of networks, those networks are huge. Now we also have a Class B, and you can see that they're kind of sliding over the network portion, aren't they? Because now we have the first 2 octets as network portion. And the last 2, octet 3 and 4, are host portions. So look at it where the blue and the gold or off-white, I'm not sure what color I got there, light brown is separating those. So now we have 16 bits of network address space and 16 bits of host address space. So 2 to the 16th power, 65,536. So we've got 65,536 networks, and each one of those networks can have 65,536 hosts in each one. So now we have more networks, but they're getting smaller. We went from 16 million down to 65,000. A little bit of a difference there, right? And then we have a Class C. And you can see we moved over the network portion one more octet. So now we have more networks. We have 2 to the what power? The 24th power, that's right. That's how many networks we have. 16.7 million or something like that. But now those networks got a lot smaller. We only have 8 bits of hosts in there. So 2 to the 8th power is 256 total IP addresses we have in that Class C address. So what I want you to know is a Class A address space, a Class A network, is a very large network, but we have very few of them. A Class B is 50-50, right? We have quite a few of them, and they're somewhat large. 65,000 addresses is quite a bit of addresses. And then we have the Class C, where we have lots of networks, but they're very small networks. And that's usually what you see in homes, small office, home offices, or Class C addresses, or private address spacing. So here I kind of broke it out to let you know what a Class A, B, C, D, and E would look like in the first or second octet. So a Class A is going to begin with either a 1 through 120, let's say 126, just so I don't get any emails saying I'm totally wrong here. All right. If, however, maybe I will put it out there, if you do the binary rules, it is 0 to 127. But we don't use 127 as a Class A address. All right, that's reserved, and we're going to see that here in just a second. So let's say a Class A is, for argument's sake, is between 1 and 126. A Class B would be a 128 to 191. A Class C would be a 192 to a 223. And now we have a Class D and E that we haven't talked about yet. A Class D is for multicasting addressing. And that's from 224 to 239. And then we have an experimental range out there, which is 240 to 254. Most of the times you're going to see A through C if you see any classical addressing at all, because we don't really do it quite this way anymore. You can still say I've got a Class A, B, C address, but it may not be, I don't know how I want to put this. We may be using something they call CIDR, Classical Center Domain Routing, where you may change where exactly the boundaries of the network and the host portions are. Because if you remember from our graphic, they lined up real nice right on the octets for A, B, and C. They may not do that anymore. All right, it may be half of the next octet, for example. That's how we do it now. So those special addresses I was talking about, all right, we're going to need to know these for security purposes because these may be on the inside of our network, and more than likely they are. If you have public IP addresses all the way to the desktop, you're setting yourself up for failure, all right? That is a vulnerability in itself. You're taking a very high risk. Remember we talked about risk analysis? That would be in your risk analysis because that's going to be a problem. So I'm going to go on a limb and say more than likely you have private address spacing inside of your network. Now, this private address spacing could be the 10 network. Like I mentioned earlier with my example, we had the 10.10.0.0 network. But anything that starts with the number 10 is private IP addressing. And you're free to use that any way you see fit. You may have the 10 network in your enterprise, in your organization, because it can support up to 16 million addresses, quite a bit. And you very well may use that. But the organization down the road or highway, different state, they may use the exact same IP address scheme that you're using. Now, how can that be possible? Because earlier I said it uniquely identifies them. So how can you have the 10 network and they have the 10 network? Well, that's private IP address spacing. This IP address doesn't go out your gateway. Remember, we talked about the default gateway of getting out of your network. Well, once it leaves your network, it doesn't necessarily have this information on here anymore on the header of the packets that are traversing through the internet. So a couple other private address spaces, 172.16.00 through 172.31.255.255, and the 192.168.00 through 192.168.255.255. Anything within those three ranges is private IP address spacing. You can use that any way you see fit on your internal network. Don't try to stick this on the external network. It's not going to work very well, okay? It's not going to be routable. So you can use this inside all day long. If you're setting up a lab in your home, you can use these IP addresses and test out your networking equipment, test out your security, test out your hacking skills or your mitigation skills, right? This is the IP addressing we're going to have. Now, I did stick the loopback on there, 127.0.0 through 127.255.255.255. Because remember earlier I said with the Class A, I don't want to get in an argument, but binarily 127 is a Class A, but we don't use that on hosts. We don't use those on those end devices because it's used for loopback testing, testing our own TCP IP stack on our computers. Traditionally, we say, hey, I can't reach so-and-so. Well, the first step is to test your own equipment, right? Don't always just blame the distant end. Maybe the problem lies with you. So you may open up a command prompt, or if you're on the phone help desk, you may ask somebody, could you open a command prompt for me and type PING space 127.0.0.1. That's traditionally what we've always used for our loopback addressing. And that would test to see if their network interface card is even working. Because if that's not even working, there's no way I need to test the communication. Don't test the line, don't test the router or the switch or the other end because I can't even get this far, right? So that's why we want to start closest to the source and move our way to the destination. That's what we use loopback addressing for. So that was IP addressing. Now we said that IP addressing is responsible for the roadmap, showing us the way, right? TCP/IP, specifically TCP, shows us how exactly to get there. Let me back up. It takes what IP says and reliably delivers that information. That's a better way of putting it. Because TCP is responsible for actually getting that data from point A to point B. It uses the information that IP provides for us to get that information there, however. That's how they work together. So now we're at layer 4, right? TCP, layer 4, transport is going to transport this information. It is reliable. TCP is connection oriented. It has a three-way handshake, all right? And I have a picture here. It's called the three-way handshake, three-step startup. And we do this when we meet people all the time too. If I met somebody or I'm introduced to somebody that I've never met before, right? I'll extend a handshake. And what I'm trying to do is synchronize. And that's what I'm talking about there in that last bullet, that three-way handshake, where you see the SYN and then an ACK/SYN and then an ACK. That stands for synchronization, acknowledgement synchronization, and an acknowledgement. And we do this. Again, I would extend my hand. I'm trying to synchronize with you, the send part. How are you doing? My name's David. They would acknowledge me. Nice to meet you, David. My name is Billy, right? So I synchronized. They acknowledged me. And now they're trying to synchronize with me, telling me his name. And I say, nice to meet you, Billy. And I'm acknowledging him. So we've established this communication now. Now we can start to actually pass some data. Because I know he's there. He knows that I'm here. I know he's listening. He knows that I'm listening. Well, for the most part, I guess you could say. But in the computer world, that's how it works. Now, in the picture there, we've got something that looks like a SEQ. That stands for a sequence number. All right, you have to have sequence numbers when it comes to TCP. As well as the internet does work, and it actually does. Some people, it's slow, it doesn't do this, and that's true. But they don't understand exactly how things are working when it comes to internet connections and how that data is actually moving. All right, I think if they could step back and see the big picture, they might be in awe a little bit more, right? And I'm talking about those non-technical users that we deal with every once in a while. But back to the sequence number. We know that everything works for the most part the best way it can. When that information leaves your computer, remember it's going to the default gateway, out to the internet. Well, the internet is not really that regulated. There's no rules necessarily. We have standards, we have the way we do things, but there's nothing that says the data has to take the same road every time, especially using TCP because it's reliable. If the information is traveling in a particular path, but something happens to that path in the middle of your communication, IP is going to jump into work and says, wait a second, routing protocols, we need to fix something. This road is down, it's blocked, it's flooded, whatever. We need to go this way now. So half your traffic went down this road, but now all of a sudden it has to go down this road and go to the next router and take a detour. Well, while that traffic's taking a detour, maybe this road comes back up. This is the faster road. So the rest of the traffic, IP is going to be like, oh, okay, routing protocol, we're good. Start sending it this way. So now what has happened? Well, we got the first piece of data real fast. Okay, but the second piece had to take a detour, while the third piece got to go on the fast road. So you may get the data in the wrong order. You may get the first piece, and then the third piece, and then the second piece. Well, the sequence numbers, they take that information and they say, wait a minute, that's not right. 2, you go over here. So it's 1, 2, 3, 4, 5, 6. It puts it in the right sequence. Because, again, you may not get there at the exact time that you're supposed to. Now, we also have something on there called a D port and an S port. Looks like sport. That's our destination port and our source port. And we're going to talk about ports here in just a minute. But ports are associated with particular applications or services running on your network. Or, in this case, running on a host somewhere, on a server. Port 80 is a common, well-known port, and that's associated with HTTP. So it looks like our host is trying to talk to a web server here. Now the S port is the source port. What door, what port am I leaving out of my computer to get over to the server? That's important because when the server talks back, he's going to reverse that process, and he's going to say, well, the destination is that port, the door on the distant end. And now the source port is port 80 because I'm leaving port 80 because you requested some web services. So that's what that stuff means there on the picture there in that 3-step startup or the 3-way handshake. Now once we're all done, we're done passing data, everybody's happy, I've gotten all my data, we took the right paths, everything's cool. We're going to shut down. Okay, we don't want to leave that communication up forever. Because really we only have a finite number of ports. There's only 65,536 ports in your computer that you can have open. So you can have 65,536 concurrent connections, which is a ton, I understand. But let's say you don't ever close those ports off. Well, I guarantee it. I know my son has visited more than 65,536 different connections in his time being on the computer. I probably have too. He just hit it a lot faster than I did, right? So we have to close those off. So we have a 4-step shutdown where the host is going to say, hey, you know what? I'm done. I'm done communicating. Let's terminate this connection. And the server will acknowledge that and say, okay, I hear you. I'll see you later. Now the server also has to shut down as well though. So he will send over a finish packet, all right? And he'll say, hey, I'm done. And I'll be like, okay, I acknowledge that. So I told him I'm done. He acknowledged that. He told me he was done, and I acknowledged that. So now our communication session is now terminated. And we don't have that port open anymore, hopefully. and we can communicate with somebody else on that same port if we wanted to, or if the computer saw fit. So I keep mentioning these ports, right? Ports are like doors in and out of your computer, in and out of your server. It's how another computer is going to reach the services that you may be providing on your particular system. Now there's a few different ranges of ports that you need to be familiar with. Well-known ports, registered ports, and dynamic or private ports. Now well-known ports are 0 through 1023. They're considered to be well-known because they're assigned by the IANA folks, all right, the same folks that take care of our IP addressing. And they're supposed to be used by privileged processes and privileged users. So that's why I can say port 80 is HTTP, port 25 is SMTP, 23 Telnet, 22 SSH, because they're just ports that, again, are well known and people memorize them. You take some certification tests and you're actually tested on those ports. So those are the well-known ports. Now registered ports, 1024 through 49151, they can be registered with the IANA folks, but they're not necessarily assigned to them. All right, you can say, well, I'm writing an application and I would like to use port 35,000. And you can register that, you can ask for it, but it doesn't mean it solely belongs to you. Your application can always request that port, but it may request, say, a range starting at 35,000. And then if that one's not available because it's already being used by your computer, it may go to 35,001, and then 35,002, 35,003, and so on. Then above that, from 49,152 through 65,533 are dynamic or private ports. These can be used freely by applications, kind of like the private IP addressing. You're free to use those any way you see fit. So be familiar with those three different ranges there.